Hello everyone, welcome back to the series of lecture for alternating current given by Mr. Ho. This is the last video, and we will be covering how a single diode can be used for half-wave rectification of alternating current. This is what a diode looks like in reality. This is what it looks like. Just to let you know, most diodes will have a gray strip at the front, right, or some other forms of demarcation to show the direction where the straight part is. Right? So if you look at this diode, it only conducts current in the direction from left to right. And the diagram equivalent is as if you have a play button, right, followed by a straight line, and it only plays in the direction, right, in which the current flows. So why do we actually need a diode? Well, previously I've mentioned to you why we need a transformer. It's in fact AC, the whole idea of AC is such that we can reduce wastage of energy through the wires. However, when you want to use the electricity itself, some objects like your handphone, like your laptop, would actually prefer a direct current. Hence, there is a need to change AC to a DC, right? And that's where the diode comes in. So let's look at how the DC changes a alternating current. First, we have a current flowing in a clockwise manner. The diode here allows the current to flow through because the button, the play button, is in the direction of the current. The arrow is in the direction of the current. So current flows. And this position of the diode compared to the battery is what we call the forward biased direction. If we, however, connect the battery in the opposite direction, we see now that the current is in the opposite direction to the diode. We call this the reverse biased, and current will not flow. So if we actually include a diode in an alternating voltage, with an alternating EMF, what we would have is that if the voltage itself looks like a waveform like this over time, when the diode is applied, we will only have the voltages or the current in the positive direction or in the forward biased direction. Simply, this means that everything below the line of zero, anything with a negative current, will be removed. So this is what we call a rectification, and more specifically, this is what we call a half-wave rectification with a diode. Now, what actually causes this to happen? How does it actually work in a diode? We will actually cover this later in the chapter on lasers and semiconductors. But for now, we can give you a brief overview. A diode is actually made of two semiconductors, P-type and N-type, fused together. And this kind of diode is called a PN junction. And they will actually have a IV characteristic as shown here. In the forward bias, which is on the right-hand side of the axis, you have this diagram where you see that past a certain voltage, this point where it starts to turn is actually called the knee voltage, your knee on the leg, K-N-E-E. Right? The forward bias is a knee voltage. Past a certain amount, the current increases by a lot when the voltage increases by a little. Right? In the forward bias, the diode is fully conducting. And in the reverse bias, right, please note that the axes are slightly different. In the forward bias, the axis is in milliamperes, In the reverse bias, the axis is actually in microamperes, which means that this line that you see, although that is slightly, it's not completely horizontal, is actually very, very close to being horizontal. Because microamperes is a very, very small amount of current. So in the reverse bias, almost no current goes through. It should be almost a straight line. And once it hits what we call the breakdown voltage, which can be adjusted and can be, sometimes it's mostly larger than your knee voltage. It can be around 1.5 voltage or more. Your breakdown voltage will happen, and the PN junction will break down. Current will flow through as if the diode was not around. Alright, so this is a brief overview. More on this in the chapter on lasers and conductors. So let us go back to the half-wave rectification with a diode. Here we have an example. We have a current, right, described by this equation. It's allowed to flow through a 12 ohm resistor. A diode is connected in series such that what you end up is this. So if the diode was not included, you will actually get a full sine wave of maximum value 9. Okay? We are asked to find the root mean square current of the rectified circuit and the average power in the 12 ohm resistor over time. Okay. So here, to find the root mean square current, we should first find the mean square current. So what you do is that you square it. Remember in the previous video, when you square a sine wave, you get a sine square wave, and it is actually rather smooth at the bottom. It's not pointy, it's smooth. However, because you remove the other direction of the current, which is the bottom, the negative direction current, the sine square for those parts will also disappear. Okay, so by squaring it, you get this. And after squaring it, right, the root mean square current, the activities you need to do is to square it, to mean it, and then to root it. So to mean this part provides another new difficulty for us. Previously, if all the other waves were still present, the mean square current is essentially halfway point, half of the maximum value. Right, 40.5 is half of 81. Right, I've done it by showing you that the areas on top match the areas below. So how do you find the mean value now when half of the wave has disappeared? Well, let's divide it into parts. If you look at time 0 to t over 2, right, the wave did not change at all. So we can safely say that for between this period of time, the average value of the mean, that means the mean square current during this period of time, is 40.5, as like before. In the other half, the second half, the current becomes 0, the current square becomes 0. We can then say that the mean square current becomes 0. Hence, if half the time you're at 40.5, the other half of the time you're at 0, we can then say that the mean current is essentially in between at 20.25, which I've rounded up to 20.3. Right, so the mean square current is 20.3 ampere square. Hence, the root mean square current is essentially 4.5 amperes. Note that 4.5 amperes is exactly half of the maximum current. Did this come about by a quirk of chance? Well, let's take a look again, right? Let's go through the whole sequence again. So you start with this diagram, the initial half-wave rectified current. You square it, you get the black curves here. You take a mean, you find that half the time is at 40, half the time is at 0, you get a mean of 20.3. But let's take this value. The previous mean square current of 40.5 is half, right? It's half of the maximum value. So if you find the mean of the rectified circuit, it is half of the previous half. It is a quarter of the maximum value. So this 20.3 is essentially I naught square over 4. This value, I say again, is I naught square over 4. So then does it come as any surprise that if you square root it, if you square root I naught square over 4, you will get I naught over 2, which is half of the maximum value. So this leads us the very wonderful result boxed up in yellow, that a sinusoidal wave, when half wave rectified with a diode, you get that the root mean square current is half of the maximum current. Okay, so this is a takeaway for you to learn at the end of this video. Next, we are asked to find the average power dissipated in the 12 ohm resistor over time. Well, average power is simply root mean square current squared times R, which just means it becomes the mean square current multiplied by R. Put in the values, we get 243 watts. So easy peasy, right? It's a simple step to do. However, I want to go one step further. How does the rectified, right? This average power is the rectified power. How does it compare to the maximum power? How does it compare to the maximum power? In previous lesson, right, we learned that for a non-rectified sinusoidal wave, the average power is actually P naught over 2. Right, so with all the full sine wave like this, up and down, you get P naught over 2 as the average power. With a rectified circuit, half of this current disappears, right? Half of this current disappears. So instead of having a full wave, you get half of the wave. So is it then any surprise that the new power should in fact be the maximum power over 4? Now, it should not come as a surprise. However, in an exam, you may be asked to find the mean power or the average power without the calculation of a root mean square current. And what I'm giving you is the hint to solve it in a faster time, in a more efficient manner. Right, so this is what we have done in the 2 lectures and in the multiple recorded videos. And this is a summary of everything. For direct current, the root mean square current will just be for constant direct current, or uniform direct current, the root mean square current is just the maximum current, since it does not change. And the mean power will just be the maximum current square times R, since the current does not change. For a sinusoidal current, we have found that the root mean square current is essentially the maximum current, I naught divided by square root 2. Same for VRMS is V naught over square root 2. The power is half of the maximum power. And in this lecture, in this recorded video, we found that for a half-wave rectified sinusoidal alternating current, the root mean square current is essentially the maximum current divided by 2. Very easy to remember. And the mean power is a quarter of the maximum power. While this is not strictly in your syllabus, it has came up before in past year exams. So let me try to describe a little bit more about a full wave rectification using 4 diodes. This looks confusing, but don't worry, follow me. If you have an alternating voltage here, let's say in this direction, the current will travel up and come to this point. When it comes to this point, it has 2 paths to move, but it sees that here there is a diode. So this diode will block the current. The current has no choice but to travel this way, to the right, down past the resistor, back left, and up back to this point. At this point, they actually have two diodes pointing in the direction that it can move. However, after passing through this resistor on the right, the output resistor, the potential at that point, at this point, will be lower than it was before. Hence, there's only one direction that it can go, which is downwards, then to the left and back up again. Let's see what happens when the voltage changes direction. When the voltage moves down, moves to the right. At this point, it cannot go through this because it's in the wrong direction. It has to move up to the right and then down across the upper resistor, back left, up back to this point. And at this point, same reasoning. The previous point junction has a higher potential than this point, so it can only travel this way, to the top, to the left, and back down. Now notice that although the external voltage direction keeps changing, the output on the resistor, on the external resistor, remains the same. It always flows from up to down, top to bottom, up to down, top to bottom. What this means is that applied voltage looking like this will then be corrected into a voltage that looks like this. Right? So this way, we do not waste half of the power. However, this is still not a complete picture, simply because if you are running a DC like this through a radio, your radio will have moments where the sound is soft and close to zero, right? You will have a fluctuating radio, and that would sound very, very weird. So what do? Well, this is not really within your syllabus, but we add a capacitor. How it actually works, you can feel free to Google about it. So if you add a capacitor across the load, what actually happens is that the capacitor will help to smooth out the curve. So instead of the curve coming back down, it gets smoothed to the other crest, goes up again because it's being charged, and comes back down again. This way, you have an output that is relatively constant. And this is how we change from AC to DC. Right, so with this, I've come to the end of my whole lecture on AC. I hope you have understood the sessions. Feel free to email me any questions, and I will see you next time. Okay, goodbye.